Hi, I'm Carla Westphal from Saddleback College, and in this video we're going to be taking a look at L'Hopital's rule for indeterminate powers. Now there are three indeterminate powers that we can get. We're basically taking a look at something that looks like this. The limit as x approaches a, or we could replace a with infinity or negative infinity, of f of x raised to the g of x. So we've got some base and some exponent. And the three indeterminate powers that we can get are 0 to the 0, infinity to the 0, and 1 to the plus or minus infinity. Now, with all of this, 0 to the 0 I can actually legally write. These two expressions that have infinities in them, I'm never going to say that anything is equal to them. I've labeled them clearly as indeterminate powers. It's totally fine to say I've got an indeterminate power of this type, infinity to the 0. It's never okay to say that something is equal to infinity to the 0, because that doesn't mean anything. Okay. But let's take a look at why these things are indeterminate powers, because that can be a little bit tricky to figure out sometimes. Okay. With an indeterminate power, basically, I should feel, based on knowing how the base and the exponent are behaving, I'm not sure where the whole expression is going. So if I look at quote-unquote 0 to the 0 here, if the base is going to 0, well, 0 to any power would be 0. So the base being 0 makes me think this should be 0. But I know that anything to the 0 power is 1, so the exponent being 0 makes me think this should be 1. So I'm getting some conflicting information. Okay. Now, if I have exactly 0 to the 0, that is 1. But if I have a limit where I've got one function in the base position that's going to 0 and a second function in the exponent position that's going to 0, that's an indeterminate form. Okay. Infinity to the 0, meaning that the base is going off to infinity, the exponent is going to 0. Okay. Well, again, anything to the 0 is supposed to be 1, so the exponent being 0 makes me think that I should be getting 1, but this base is really, really big. Now, if the exponent, remember it's not exactly 0, it's just close to 0. If the exponent is close to 0 and positive, I've got a really big number to a positive power. That would mean I'd expect something big. If the exponent is close to 0 and negative, a negative exponent would mean I'd be taking the reciprocal of this really big base. I'd be expecting to get something small. So lots of possibilities here, definitely need some investigation. This last one, 1 to the plus or minus infinity, I think is the toughest one to spot, because you see a 1 in the base and you say, well, 1 to any power is 1. Duh. Okay. But what's interesting is 1 is the cutoff between things that get bigger when you take them to a big power and things that get smaller when you take them to a big power. So if I have a number that's a little bit bigger than 1, like even 1.0001, if I took that to the millionth power, I'd actually get something pretty big, because as long as my base is bigger than 1, I'm getting exponential growth. But 0.999 is also close to 1, but that's smaller than 1. And when I take something smaller than 1 to a big power, I'm getting exponential decay, and it's getting smaller and smaller and smaller. So if 1 is the boundary, where things on this side get really, really big when I take them to a big power, and things on that side get really, really small when I take them to a big positive power, and of course those roles are just reversed if we switch the sign of the big exponent, make it a negative infinity, well then if I'm close to the boundary, I really don't know where I'm ending up. So all of these are going to be things that are going to require that we use L'Hopital's rule. But again, L'Hopital's rule only applies to indeterminate quotients. So before I can use L'Hopital's rule, I have to do some algebra to convert from an indeterminate power to an indeterminate quotient. Now, even though we've got three different indeterminate powers, the same basic technique works for all of them. So let's just take a look at an example. Let's suppose I wanted to take the limit as x approaches 0 from the positive side of sine x to the x. So if I take a look at this, the base, sine x, is approaching 0. The exponent x is approaching 0. So we've got an indeterminate power. So I want to do some algebra that's going to allow me to somehow convert this to a quotient. And one of the things I might be thinking is it would be really cool if I could bring that exponent down, get it out of that exponent position. And a thing that allows me to do that is logs. Rules of logs allow me to bring down powers. Just remember, if I have the log, well, let's use natural log. If I have the natural log of a to the b, that's the same as b times the natural log of a. That gives me a way of going from a power to a product. And we already know how to go from an indeterminate product to an indeterminate quotient. The problem is, I can't just go around taking the natural log of something just because I want to, because that's going to change it. So if I take the natural log of this, I don't have the same expression anymore. No reason to expect that I'm going to get the same limit. So what I'm going to do instead is something that we do a lot in math. I'm going to do something, but then I'm going to undo it so that I'm essentially doing nothing. So I'm going to say that this is the limit as x goes to 0 from the positive side. Now I'm starting with sine x to the x. I'm going to go ahead and do something to that. I'm going to take the natural log of that. But then I'm going to undo that. And how do I undo taking the natural log? I would exponentiate. So I'm going to take e and raise it to this power. Notationally, this might be a little bit new. I'm going to write that as exp of the natural log of sine x to the x. This is just an alternative notation for the exponential notation. Okay. So let's just make a little side note here. Exp of x is just another way of writing e to the x. Notationally, it's really nice in this case because when I write something in the exponent position, it's in that superscript position and it's usually kind of small and I've got less space to write it. So this just allows me, when I have a complicated thing that I want to put in the exponent position, to keep it down on the main line of text. Okay, so I haven't changed it now because I took the log, but then I undid taking the log. But now I can use rules of logs to bring that x down in front. So I can say this is the limit as x goes to 0 from the positive side of exp of x times the natural log of sine of x. So I've got this product now, right here. And if we've done things right, this should be an indeterminate product. One factor should be going to 0. One factor should be going to plus or minus infinity. Let's check. X was going to 0. Sine of x was going to 0. And also from the positive side. So the natural log of that is going to negative infinity. So we do have an indeterminate quotient. Okay. But now this is kind of interesting because we have an indeterminate product. I misspoke. We have an indeterminate product, not yet an indeterminate quotient. But I've got this exponential function here. Well, the exponential function is continuous. We have a rule of limits that says we're allowed to bring that limit inside of a continuous function, provided we get something that makes sense. Okay. So I'm going to say that this is equal to exp of the limit as x goes to 0 from the positive side of x times the natural log of sine x. And I'm just going to make a note. I said we can do that if what we get makes sense. If this limit ends up being a finite number, I've just got the exponential function evaluated at a number. That's totally fine. But if this limit ends up being infinity or negative infinity or does not exist, I can't plug in any of those things to the exponential function. So this step right here is legal if the limit is a number. The rule is it has to be a number in the domain of this function, but the domain of the exponential function is all real numbers. So if we get a number, we're covered. Okay. Now, in this example, I'll tell you, I'm going to give it away, we're going to get a number so that this is going to be legal. We will have to adjust our work if we get infinity or negative infinity, and I'll show you that in the next video that I'm going to create. And that gives you an alternate way of notating things that you could use in this case, but I kind of like writing the exp and the log together like that. All right, so now I'm going to convert this indeterminate product to an indeterminate quotient. So I'm going to say this is exp of the limit as x goes to 0 from the positive side. The natural log of sine x is the more complicated factor, so I'm going to keep that, I think, on top. And then, rather than multiplying by x, I'll divide by its reciprocal, 1 over x. So let's just confirm that we have an indeterminate quotient. We said the natural log of sine x was going off to negative infinity. 1 over x will be going to positive infinity. So we have an indeterminate form of type, quote unquote, negative infinity over infinity. And so we can use L'Hopital's rule. All right. So using L'Hopital's rule, we're going to get exp of the limit as x goes to 0 from the positive side of the natural log of sine x. When I take the derivative, I'm going to get the reciprocal of sine x times the derivative of sine, which is cosine. 1 over x, remember that's just x to the negative 1, so that when I take the derivative, I get negative x to the negative 2, which I can write as negative 1 over x squared. Okay, so let's do a little bit of simplification before we look to see whether we're good to go or not. Okay. So this is exp of the limit as x goes to 0 from the positive side of 1 over sine x times cosine of x times negative, I'm just going to bump that negative to the front, 1 over, times x squared. Because if I flip and multiply, that's going to become a negative x squared. Now, if I take a look at this, I've got a couple of options here. If I wanted to, I could rewrite this as cosine over sine being cotangent. But I'm going to just notice that since sine x is going to 0, this piece as a whole would be going to negative infinity. Cosine x, though, is going to 1, and x squared is going to 0. So I'm just going to rearrange things a little bit. I'm going to notice that this is exp of the limit as x goes to 0 from the positive side, negative x squared over sine x. I put my two problem pieces together. These are the pieces that are going to 0 and contributing to an indeterminate form, times cosine of x. This is the nice well-behaved piece. This is just going to 0. Okay. So what I'm going to do is, rather than apply L'Hopital's rule to this whole thing, which I could do, but then I'd be thinking of this as one fraction where the top was negative x squared times cosine, and I'd have to use product rule and all of that. I'm going to just split this up. I'm going to say this is exp of, I've got a product. I'm going to take the product of the limits. The limit as x goes to 0 from the positive side of negative x squared over sine x times the limit as x goes to 0 from the positive side of cosine of x. This is an important strategy here. If you have a bunch of pieces, it's the pieces that are going to zeros and infinities that are leading to the indeterminate form. If you've got a piece that's nice and well behaved and going to a finite number, very often you can separate that piece out to simplify your calculations. So now, for this piece, top's going to 0, bottom's going to 0, I'm going to use L'Hopital's rule here. This piece, I'm just going to plug in 0. Okay. So I can say this is exp of, by L'Hopital, the limit as x goes to 0 from the positive side of negative 2x over cosine of x, times the limit of cosine x is just cosine of 0, which is 1. Okay, excellent. So now we can evaluate by just plugging in 0, because this is just going to be 0 over 1. So we get exp of 0 over 1 times 1, which is just exp of 0, which is e to the 0, which is 1. So this whole limit ends up just being 1. Okay. One quick note on the notation here. The most common wrong answer I tend to get when I assign a problem like this is 0. Because people do all of this work and then they forget that they were supposed to exponentiate, which remember we had to do in order to undo the log. That's why it's my preference to be writing this exponential function. You'll notice I've written it every single step from the very beginning so that it's on my mind and I'm not likely to forget it. Okay. One option, and your textbook shows both options here, one option at the beginning would be to say, let's let y equal sine x to the x, then the natural log of y is equal to the natural log of sine x to the x. Here, I just took the natural log without exponentiating to undo it. The reason I could do that here is because I was working with both sides of an equation. So I was doing the same thing to both sides, and you're allowed to change an equation if you do that. So that's totally legal, okay? And it's legal then to try to take the limit of this, but then you have to remember at the end, what I've taken the limit of is the natural log of y. What I wanted to know was the limit of y. You need to exponentiate. So my preference is to write this all along. But you'll see lots of people who do it by simply taking the log first, working with this, and then remembering to exponentiate at the end. All right, that is our first indeterminate power.